Welcome to the third tutorial for the agents. In this tutorial, we will be adding new functionalities for the image classifier agent that we created in the last two tutorials. The focus of this tutorial will be the multitasking feature of the agents, which allows them to support several tasks concurrently. Also, we allow sharing nodes between the graphs of the tasks of a given agent, which results in saving resources while enhancing the performance of the agents. In particular, we add two new tasks to our image classifier agent, a visualization task and evaluation task. Let's start changing our agent. First, we add the visualization task and we name it Viz. We want to use this task to see the train classifier model by the first task, which was the train task, in action by adding a logger node. From the drop-down menu, we select the Viz task in order to change its graph. The Viz task being the second task of this agent, you have access to all the nodes of the first task of this agent via the Shareable Nodes tab. Here you see all the nodes of the first task of the agent. Note that every node coming from the previous tasks is colored red. Another feature of these shareable nodes is that you can only change their settings in the original task that they are defined in, not in the following task that they will be used as shareable nodes. The first node that we borrow from the first task is the MNIST net node, which is the classifier network. Next, we add the softmax node from the first task that takes the logits from the MNIST net node and gives us the softmax distribution. We add a new dataset node to generate batches as the source of data for the other nodes. We set the built-in dataset parameter to MNIST in order to use the internal MNIST dataset of the platform. We set the train parameter to false so that the test split of the dataset will be used instead of the train split. We add image and label keys to the keys parameter so that the output of the dataset node will be a dictionary with two keys, image and label, where the image key refers to the image tensor and the label key refers to the label tensor. Otherwise, the output of the dataset node will be a tuple of length 2, where the first entry is the image tensor and the second entry is the label tensor. Finally, we set the batch size to 32. We rename our dataset node to VizTestMNIST. We add the pick image node from the first task and use it as an adapter node between the dataset node and the MNIST net node. Essentially, this node takes the dictionary generated by dataset node and picks the image tensor from it and passes it to the MNIST net node. Next, we add a logger node to visualize the image and the ground truth label from the dataset node and the predicted softmax from the softmax node. The first DB field is corresponding to the first incoming edge of this logger node, which is the dataset node. We will be adding two DB field logs for these DB fields. one for the image and one for the label. The first DB field is for the image, and since this is an image, we choose the field type to be image. The outer index and inner index parameters are set to 0 because the dictionary generated by the dataset node will be wrapped inside two nested lists where each list has a single entry. Here, outer index refers to the index for the outer list, and the inner index refers to the index for the inner list. Finally, we set the key parameter to image, which is the key for the image tensor in the dictionary generated by the dataset node. Next, we add the DB field for the label in the dictionary generated by the dataset node. We connect the softmax node as the second incoming edge for the logger node. We add the DB fields for the softmax node. In this DB fields, we add a single DB field config for the predicted softmax. We set the field type for this log to be number. We set the outer index and inner index parameters to 0 since the predicted softmax by the softmax node will be wrapped inside two nested lists where each list has a single entry. We do not need to set the index and key parameters since the picked up object by the outer index and inner index parameters will be the softmax tensor and not a dictionary or not a tuple. Let's update our system with this new version of the agent. Next, we need to modify our job. The sessions parameter specifies how to execute the system associated with this job. Using the sessions parameter, you could execute several sessions. That's why the sessions parameter is a list of session configs. Currently, our job has a single session that trains the image classifier network for the MNIST dataset. The system task parameter of this session config is set to MNIST, which results in executing of the MNIST task of the system. The agent tasks parameter specifies which tasks of the agents in the specified system to be executed. The system task MNIST has a single agent named MNIST referred by key 0, and that single agent has two tasks, the train task and the viz task. Here, as part of this session, we want to execute its train task referred by value 0. The key 0 parameter refers to the name of the agent, and the value 0 parameter refers to the task of that agent that we want to execute. Okay, now we want to add a second session that visualizes the prediction action of the trained model by the first session. In other words, the first session trains the model and the second session takes that model from the first session and visualizes its prediction. We name this new session Viz. We set the system task parameter to MNIST because that is the system task that has our MNIST classifier agent. The agent tasks parameter is a dictionary of the names of the agents in the specified system task to those tasks of the agents that we want to execute. Here we want to execute the viz task of the agent MNIST. That is why we set the key 0 parameter to MNIST and the value 0 parameter to viz. When we try to run this job, we get this error message from the system saying that the agent MNIST has only the train task and it doesn't have the viz task. It is because we forgot to update the system parameter of this job. We update the system of the job to get the new version of the system. Let's run the job. The job first executes the first session, which trains the deep learning model. After that the training is done, the job executes its second session and changes its status from running to finished. The train loss logger and train eval logger are from the first session executing the train task of the MNIST agent. The viz logger is from the second session executing the viz task of the MNIST agent. Here each row has the input image, the predicted softmax, and the ground truth label. Essentially, the train model by the first session is being used in the second session to run predictions for these input images. This was possible because of sharing the classifier node between the train task and the viz task of the MNIST agent. Next, we will add an evaluation task to the MNIST agent. We name it test. We have access to the shareable nodes from the two previous tasks. We add the MNIST net node and the softmax node from the shareable nodes. We add a new dataset node for the test MNIST dataset. We set the built-in dataset parameter to MNIST so that the internal dataset of the platform will be used here. We make this dataset node to output the test split of the MNIST dataset by setting the train parameter to false. We set the batch size to 1000. We make this dataset node to output a dictionary of example features with key image for image tensors and key label for label tensors. We use the pick image node to pick the image tensor from the dictionary generated by the dataset node and pass it to the MNIST net node. Finally, we add an evaluation node to compute the accuracy of the predictions made by the MNIST net node over the MNIST test dataset. We attach the dataset node and the softmax node to the eval node. Next, we need to set the eval parameter of the eval node. We set in node 0 parameter to y to row corresponding to the incoming edge from the dataset node. We set in nodes one parameter to wipe corresponding to the incoming edge from the softmax node. We set the wipe in node parameter to wipe to refer to the incoming edge from the softmax node. The wipe outer index and wipe inner index parameter are set to 0 because the softmax tensor by the softmax node will be wrapped inside two nested lists where each list has a single entry. The picked up object by the wipe outer index and wipe inner index parameters will be tensor, therefore the wipe type is set to tensor. The y2ru in node parameter is set to y2ru to refer to the incoming edge from the dataset node. We set the y2ru outer index and y2ru inner index parameters to 0 because the dictionary generated by the dataset node will be wrapped inside two nested lists where each list has a single entry. Because the output of the dataset node will be a dictionary, we set the y2ru type to mapping. Setting the y2ru type to mapping, we need to specify the key for the label in the dictionary by the y2ru key parameter. Finally, we choose accuracy as our evaluation metric. Here we make sure that y2ru and ypred correctly refer to the incoming edges from the dataset node and the softmax node. Given that the test MNIST dataset has 10,000 examples and we chose the batch size to be 1,000, in order to cover all the examples in the test MNIST dataset, we need to increase the number of the steps of the agent from 1 to 10. Let's update our system with this new version of the agent. Now we need to update our job. First, we update the system to its new version. Currently, our job has two sessions, one for training and one for visualization. We add a new session for evaluation. We set the key 0 parameter to MNIST and the value 0 parameter to test in order to execute the test task of the agent MNIST. Let's run the job. The job first executes the train session, which is the first session in the list of the sessions parameter. After finishing the train session, the job executes the visualization session and the evaluation session, and after finishing them, its status changes from running to finished. The terrain loss logger and terrain eval logger are from the first session. The viz logger is from the visualization session. The test eval logger is from the evaluation session and shows the accuracy of 97% over the test dataset.